Welcome, friends. So, in the last session, we have started discussing the sinusoidal response of series RL circuit, where we have seen the current response is roughly represented by this waveform as shown in figure 11. Okay, so it has three phases. First phase is subtransient period, then transient period, and steady state period. So in the subtransient period, we have most significant information, which is the transient behavior of that electrical network, and there on we have transient period and steady state period. And before switching, the response was found to be quite steady and within very small range. Okay, it's a normal rated current. Okay, however, whenever a disturbance comes, it may be in terms of fault or maybe in terms of some other form, then we observe that sudden rise in the current happens, and that is clearly understood. It is a transient nature disturbing our performance, disturbing the performance of the electrical network quite badly. And more you give time to the electrical system due to the self-healing characteristics of the electrical network, the oscillation or the effect of the transiency dies down with the time, and it will stay steady at the some sinusoidal varying quantities. However, the magnitude is quite large because we have fault still persisting in that system. Okay, so in this way we can conclude this event. So let us continue our discussion with the series RC circuit. So similar, we can analyze the circuit similarly. So we have a voltage equation. So now in this time, our KVL equation will be slightly changing. Though instead of L di dt, we have 1 by C integration it dt. So if you take derivative of this equation di dt, so this R should be divided both the ways, just like this: Em by R sine omega t plus theta equal to it plus 1 by RC integration 0 to t it dt. So if you take derivative of this equation, this it becomes di dt. 1 by RC integration it dt becomes 1 by RC it, and this Em by R sin omega t will become omega m by R cos omega t plus theta. So we have two forms, one is transient component, another one is steady state component. So we have transient component, so we make this equation equal to 0. So we get the solution quite directly, straightforward, which is it, that will be is equal to k into e to the power minus t by tau, where tau becomes time constant, which is equal to RC in case of a series RC circuit. Now to evaluate IS, we follow the similar procedure. We equate it with the Em sin omega t plus theta. Then we take the derivative di dt plus 1 by RC it is equal to omega Em by R. Now the solution becomes I is equal to A cos omega t plus theta plus B sin omega t plus theta. So we should get the similar process as we have discussed previously. We should get di dt. Then from there we substitute di dt and it in this equation, equation 38. When you get cosine terms together and sine terms together, then we can compute or we can compare this with the right hand side. So right hand side, in this case we have a cosine. So this case for series RC circuit, B by RC minus omega A must be 0. From there you can get B is equal to this omega RCA, and with the sign terms together you can get A by RC plus omega B, that is equal to omega EM by R. So if you substitute B in this equation, so we will get an equation like this. So from there you will get A is equal to this form, A is equal to 1 by omega C divided by R square plus 1 by omega square C square into EM. Now what is 1 by omega C? 1 by omega C is equal to XC, and this is equal to R square plus XC square. So very similar sort of expression in this case also. So it is XC by Z square into EM. So we will write this equation as XC by Z into EM by Z. So for similar, B is equal to this R by R square plus 1 by omega square C square into EM. So we write B is equal to R by Z into EM by Z. So Z is equal to, as you can see, R square plus 1 by omega square C square. So A is equal to EM by Z. Now XC by Z, previously from the power triangle, if this is R, this is XC and this is Z. So if this is phi, so XC by Z is nothing but sin phi. So A becomes EM by Z sin phi, and R by Z, B is equal to R by Z into EM by Z. So R by Z becomes cos phi. So B is equal to EM by Z cos phi. So if you substitute the value of A and B in the actual equation 26, you will get EM by Z sin phi cos omega t plus theta plus EM by Z cos phi sin omega t plus theta. So I will be is equal to EM by Z sin omega t plus theta plus phi. So therefore the total solution will be IT plus IS. So we will get a similar sort of solution in this case as well. Now we can continue, or we can do our analysis for a series RL circuit in this same fashion. So I invite all of you to do your exercise by your own for series RLC circuit. You should adopt, or you should follow the same process to get the total solution. Okay. Now let us solve one problem with this transient response with sinusoidal excitation. And now in this problem it is said a 50 Hz 400 volt peak to peak sinusoidal voltage is applied at t is equal to 0 to a series RL circuit. Okay. So we have a sinusoidal voltage source. It is applied at t is equal to 0. So switching instant, it is switching instant is 0. So we have R is equal to 5 ohm and L is equal to 0.2 Henry. Obtain the expression of current. So you should evaluate the moment you press the switch, you need to obtain the expression of current. So from the previous study, we have the expression of current is this. Now what is the value of Z? Z is equal to root under R square plus omega square L square. So R square means 5 square plus omega square L square. Now omega means it is 314 into 0.2. L means 0.2 Henry. So it is square. If you solve this, you will get Z is equal to 63 ohm. Roughly, it is equal to 63 ohm. So from there, phi can be written as tan inverse phi. That can be written as tan inverse x by r, or cosine inverse 5 by 63. To solve, it will get 85.4 degree. Now, why cos inverse 5 by 63? Because 5 represents R and 63 represents Z. So, cos inverse R by Z becomes 85.4 degree. Or if you write in terms of 10, it should be X by R. Okay, it should be X by R, perpendicular by base. So, it is R, it is X, and it is Z. So, if you represent in terms of cosine, so it should be R by Z, and if you represent in terms of tan, it should be X by R. So in the problem itself, it is written, that is why 62.8, which is actually X, divided by R, which is 5. So if you evaluate, it is 85.4 degree. Now let us consider theta is equal to 0. We consider switching time as equal to 0. Right? So if you substitute those values, now what will be the time constant? It will be, total solution will be k into e to the power minus t by tau. Now what is tau? Tau is equal to L by R, which is 0.2 by 5. So it will be 0.04 second. So it will be actually 0.04. So it will be k into e to the power minus t by 0.04, which is equal to k into e to the power minus 25t. And the steady state response, it will be Em by Z. So Em is given 400 peak to peak. Z we have evaluated 63. So sine omega t plus theta, theta is 0 minus phi, phi is evaluated 85.4. So it is the solution. I is equal to e to the power minus 25t plus 400 by 63. It will be roughly 6.35 into sine omega t minus 85.4. Now you should evaluate the value of k. So what is that? Now before switching, there should not be any current. Before switching, there should not be any current. So we can write I0 minus will be 0. So just after the switching, I0 plus is also 0. At t is equal to 0, at t is equal to 0, we have I is equal to 0. So if you substitute I is equal to 0, therefore k into e to the power minus 25 into 0 plus 63.5, not 63.5, it is 6.35, 6.35 sine 6.35 sine. Now omega t, t is equal to 0, so it will be 0 minus 85.4. So with this, if you solve this, you will get the K value is equal to 6.323. So the total solution becomes this. The total current expression including transient response and steady state response is this. Now also there is another part. Also evaluate the transient value of the current at t is equal to 0.01 second. So you need to just, in order to solve t is equal to 0.01 second, so just you need to put I at t is equal to 0.01 second. So you just need to put t is equal to 0.01 in this expression. So 6.323 into e to the power minus 25 into 0.01 plus 6.35 sine 314 into 0.01, because 314 is omega and 01 is t. Omega t minus phi 85.4 degree. So if you solve, it will coming out to be 4.93 ampere. 4.93 ampere. So you can understand that at t is equal to 0 second, the current was 0. However, within some time, 0.01 second, that is within half cycle time, the current becomes 4.93 ampere. 4.93 ampere within half cycle time. So this is a good illustration of the transient response of a series RL circuit. So with this, I am ending this part here. So module 7, that is the transient response of the electrical network, is more or less covered. Now this, let me clearly tell you that to solve this transient analysis of an electrical network, we have two approaches. First approach is based on differential equation, and this differential equation approach is mainly discussed in this session or in this module. Now we have another approach which is called Laplace transform approach. In next two modules we will solve the Laplace transform approach and we will see the Laplace transform approach. In the next module, which is module 8, we will study what is Laplace transform and what is the if you consider different signals, then if you apply Laplace transform on those different signals, what will be the output? Because to solve transient response using Laplace transform technique, so you should have some idea about Laplace transform technique, what is Laplace transform technique and what is its end role, how it plays, how it influences. Okay, so next module is mainly the introduction and overview of Laplace transform, and in the module 9 we shall see the application of Laplace transform in the transient response analysis, and there we shall apply the technique this directly to solve this transient response analysis quite effectively. So for the next two modules we shall discuss mainly on the Laplace transform. So with this I am ending this part. Thank you for watching.